Well, ladies and gentlemen, welcome back. And now our next session is going to look at three innovative methods of electricity generation. First of all, small modular reactors, fuel cells, and thirdly, tidal power. And the first speaker this afternoon is Dr. Fiona Rayment, Fuel Cycle Solutions Director at the National Nuclear Laboratory. And Fiona is a chartered chemist and a Fellow of the Royal Society of Chemistry, and she's had 20 years nuclear industry experience, working primarily within technology, operations and strategic planning across a number of different nuclear sites, both in the UK and internationally. Fiona will talk about the pros and cons of small modular nuclear reactors, illustrating characteristics of the current designs being developed, and she'll also address the challenges and timescales for reaching commercial development. Fiona.
Okay, good afternoon, ladies and gentlemen. Today, it's quite a challenge to talk about just one small component of a system. So in terms of what we do at the National Nuclear Laboratory, we get involved in a whole, I guess, the totality of the fuel cycle, from fuel manufacture all the way through to reactor design and operation support, and also looking at waste management and decommissioning. But today, I've been asked specifically to talk about small modular nuclear reactors. So that's what I'm going to talk about today. So there's been an increasing interest in small modular reactors over the last few years, both in the UK and also internationally. There's a number of reasons for that, and I'll talk about that through my talk. What I'll do is I'll give you a brief survey of some of the small modular reactor systems, look at some of the pros and cons and timescales, and also look at a whole systems view, actually thinking about the economic competitiveness of such a system and taking into account some of the engineering aspects. So first of all, what is a small modular nuclear reactor? Well, there's a number of definitions that apply, but the International Atomic Energy Authority stipulates that it's a reactor that basically has an output of less than 300 megawatts electrical. That being said, there are a number of reactors that are still classified as small modular reactors that are slightly larger than that and can, I guess, give output up to about 500 megawatts electrical, and they're still recognised as small. But a number of the designs range from 10 gigawatts electrical all the way through to 600 megawatts electrical. The modular itself implies that there's going to be some multiple units that are maybe grouped together, sharing common facilities and staff. There are applications, however, that actually are single units, and the modular nature is more about the actual construction of the facility. Or there's also multiple units that are actually considered that can actually make up a large power station. So instead of actually taking one large nuclear power plant, taking a number of small modular nuclear reactors and putting them together in series to create a larger nuclear power plant. And of course, there's an implied assumption associated with this that there's actually going to be some economic savings associated with going down this multiple units route. So, in terms of some of the niche applications, first of all, just looking at energy generation, there are a number of multiple unit modular power plants that are being looked at. And taking maybe a unit that's maybe about 300 megawatts electrical, multiplying that up by 4, getting yourself up to about 1,200 megawatts electrical as an example. There's also a number of small plants that are being looked at on their own, so actually just one actual unit itself. And that's because of the whole issue surrounding energy decarbonisation. As we know, it's a global issue, and looking at a number of options that need to be considered from that perspective. So some people are actually looking at just a small modular plant in order to deal with some of their energy needs at the moment. And in terms of that, I'll talk about this later in terms of some of the economies associated with that. In addition to that, they're also looking at other things outside of just producing electrical energy. So, for example, in some places, there are some people looking at desalination plants and able to actually create power in order to enable desalination. And so small modular reactors are a potential technology to enable that to happen, as well as being looked at for also various heat applications as well. They're also being looked at for power sources in remote locations. Some of the small modular reactor units themselves are pretty low power, but actually are quite handy in terms of they're small in size, they're multiple units, they are modular in design, so can actually go out to remote locations. And as well as all of that in terms of the land, there's actually various nuclear power plants that are being looked at now in a modular nature for marine application. So there's a number of barge-mounted units that are also being evaluated as well. So I don't know if you can see some of the information here on the right-hand side of this slide, but what I'm trying to show here is that there's a load of small modular reactor designs that are currently being evaluated. And basically, it's being dominated by the light water reactors that people see currently across internationally in terms of the current nuclear design. And basically, the LWR design is the current nuclear design. It's based on existing design experience. And as a result of that, you would assume that it's actually closer to deployment than any other. But that being said, they're still about 10 years off in terms of any sort of small modular reactor that could actually come onto the bars today and actually be utilised going forward. So that's where we think we're at, probably about 10 years off. The actual chart on the right-hand side highlights a number of reactor systems. You'll see that, as I've highlighted here, the capacity does vary quite substantially from 10 megawatts electrical all the way up to some in the region of 300 odd megawatts electrical. And as I've highlighted, a lot of them are LWR, the pressurised water reactor systems. There are also systems that are not pressurised water reactor systems, and I'll come on to that in a minute, but a lot of the development work associated with the systems that are not pressurised water reactor systems are being led much more from the academic side of things as opposed to actual developers getting involved at this stage. Now, one of the things I should highlight is it's quite difficult to compare some of the pros and cons associated with these systems because they're actually all at different stages of development. And at the end of the day, there will only be a few of the proposed designs that are highlighted here that will ever make it to commercial deployment going forward. So I've got a few systems that I'm just going to show you just to give you some comparisons. So in this particular case, there's two systems. One is by NuScale and the other one is by Holtec, both United States organisations. One of them 45 megawatts electrical energy, the other one 145 megawatts electrical energy. Both of them pressurised water reactors. Both of them actually looking at a number of passive safety features, including natural circulation within the core itself. Both of them using modularised units in terms of the actual fuel assembly, so 17 by 17 fuel assemblies, and actually looking at having a core height to enable that natural circulation within the core and enable that passive safety. Another couple of comparisons, looking at the B&W mPower reactor and the Westinghouse small modular reactor. Again, both pressurised water reactors, different levels of energy output, 180 megawatts electrical for the mPower system, 220 megawatts electrical for the Westinghouse SMR system. In this particular case, using forced circulation for cooling within the system in comparison to the others, which was natural. But again, both of them using modularised fuel assemblies, again the 17 by 17 fuel assemblies, in terms of how they're actually set up within the core. Looking at a couple of examples that aren't pressurised water reactors, there's a General Atomics reactor that again is around 285 megawatts electrical, that's actually a high temperature reactor. Where these types of reactors come into their own is when you actually start to look at maybe for some additional heat that you're maybe needing for process heat. as opposed to just looking for electricity generation per se. And this particular reactor system uses a spherical fuel in terms of how it works, and uses a gas coolant in terms of the actual coolant within the core. The other one I've highlighted here is the PRISM reactor, which is a GE Hitachi version. It's actually one of the reactors that's currently being considered by the Nuclear Decommissioning Authority for the plutonium disposition programme. In this particular case, I've highlighted that it's 622 megawatts electrical, but it's actually two reactors that are put together in parallel, so they're both 311 megawatts electrical, so hence the reason why it's still considered as a small modular reactor system. This is a fast reactor, which actually uses sodium as a coolant, liquid sodium as a coolant, and it actually uses metal fuel. So some various types there. I haven't got time to talk about all the different types that exist, but there's just a flavour for some of the reactors that are currently being considered at the moment within various design phases. So, what are some of the SMR economic levers? Well, in terms of the whole concept around the construction costs, with the modular reactors, there's a number of key advantages. First of all, it's a simplified design. It's bringing together an integrated design within the actual primary circuit of the reactor vessel itself. The increased modularity and the actual factory build is a key component, because here you're actually able to make the actual modular units at the factory site, as opposed to actually bringing actually making the modular units actually at the site where the reactor is going to be used. So there's I guess an economic advantage associated with that. Also, with the fact that you're making multiple units, there is an economy of scale associated from that with a mass production perspective. And also, when you actually start to look at some of the advanced manufacturing techniques that you can bring into play, when you actually start looking at the modular nature of the facility. It also impacts on shorter construction times, especially when you get to multiple plants of a kind as opposed to first of a kind. The other advantage is around the finance costs. So looking at cost of capital versus capital cost, in terms of the cost of capital, the concept there is that because you've got a modular system and you're actually going to have a few in parallel with each other, when you actually build one, you construct one, you can put it on the bars quickly. You can actually start to generate electricity. So you're actually starting to get your cash flow moving sooner, earlier, than what you would with maybe a larger power plant in terms of taking that forward. And as the second one goes on the bar, you start to generate more cash, etc., etc. In addition, in terms of capital costs, well, there's shorter construction times. So shorter construction times lead to reduced costs associated with that too. Then on the operating and maintenance costs, there is a view that the simplified design will reduce the maintenance needs, and as a result of that will reduce the costs associated with that. And also, the current models assume that these multiple modules will be able to run with about 400 to 500 strong workforce in comparison to a large plant, which is around 1,000 strong workforce in terms of the requirements there. And of course, as I've highlighted, because of the fact that it is a modular nature, and you're actually starting to use a key supply chain companies within a particular area, because you're actually looking at smaller units, there is a view that you can actually start to use more organisations, more companies, because they're able to manufacture these smaller components. But there are a number of challenges. And a key point is that all of these economics are currently theoretical. And they need to be demonstrated to work in practice. And it's the biggest challenge that any of these small modular reactors face. It should be noted that there's no current SMR that's had a complete engineering design, which would actually enable a full cost estimate to completely be validated at this moment in time. So the economic figures for SMR designs at the moment are projections. They're based on nuclear power plants, but they are projections in terms of where they are right now. So the point worth noting is that the economics look good, but it's at a conceptual stage that they need to be validated in terms of taking it forward. In terms of, so just finally, in terms of a couple of system features, a key point around the small modular reactors is around the simplified or passive safety of the system. So the integral systems layout has an ability to be able to enable the system itself to be more passively safe in terms of the simplified nature. So there's less moving components within the system in terms of its use. There's also larger coolant masses which are being used for to enable, I guess, any sort of loss of coolant accident. If you actually use large coolant masses, the benefit associated with that is it will actually take a longer time for any differential in heat to actually come to effect, and therefore you're actually rendering the system an awful lot more safe in comparison to previous systems that have existed. The high vertical heights that I've talked about within the core itself enables natural convection, and that again is a key passive safety feature. And of course, natural convection is being used in some of the reactors in terms of normal operations as well. There's also some challenge associated with needing to address multiple units, though, in close proximity. Some of the modular systems are deemed to be much safer because they're smaller systems, but if you actually start to put them in parallel with a number of other modular units, then the challenge there is that you're starting to get to the stage that you actually have to have a safety feature that's similar to a large nuclear power plant. Some other key aspects are the fact that a lot of the cores nowadays are actually going to be sited underground, which of course is an advantage from a number of places in the world where you don't have major seismic events. And that's a real opportunity in terms of addressing a key safety feature here. But if you start to look internationally, underground siting of course might not be the preferred option going forward. Another aspect is the longer refuelling cycles. So there's a number of fuel cartridges that are being put in now to these systems in terms of how they're designed anyway, that will actually last for a period of 4 years before you actually have to refuel. And there's actually even a number of systems now that are being looked at to be autonomous, where you actually can change cartridges autonomously and enabling the actual system itself to be operational for a sort of 15 to 30-year time horizon. But with any system, again, when you're starting to design something from scratch, there are some challenges. It comes back to actually the designs needing extensive validation. So integrating the plant components may increase the importance of interactions between the components, and that needs to be validated further before we can really understand where we're up to with that. The small size doesn't necessarily improve safety. The small size itself is key in terms of the economic viable nature of the power plant, but actually the small size itself, it's a nuclear power plant, so it still needs to be basically adhering to the most rigorous safety standards. I talked about natural circulation, but there's still quite a lot of R&D required to actually validate that natural circulation within the reactor core and actually get it to a level of understanding with people as to how the natural circulation system actually behaves over time. I've flagged up the fact that the underground siting may improve protection in some scenarios, but there are certain geographical locations in the world where it may not be the best option based on whether there's a seismic event that could be predicted within that area. So, going forward, I think that SMRs do represent an alternative to large-scale nuclear power. It also has a good fit with developing countries where maybe there isn't the same sort of level of cash around in comparison to maybe what there is in countries like in the developed world. It does expand options for nuclear contribution to energy decarbonisation, but there is still a lot to do in terms of the economic and technical challenges associated with it, and specifically getting to a situation where the plants themselves are properly validated in terms of how they will operate over time. So I guess the bottom line is that once we get to the stage that we've got a key engineered design going forward for the small modular reactor systems, like any new design, it starts off with a number of advantages, and as you go forward and validate that design, the question will be whether the engineering enables the advantages to remain, or whether the advantages start to dissipate over time. Thank you.
We don't want to put you on the spot, but perhaps you could tell us your best forecast as to when we'll be getting electricity from an SMR.
Well, I mean, I think that 10 years is a good prediction, and I do believe it'll be a pressurized water reactor. It won't be any of the other, I guess, more exotic designs at this stage, and it will be based on the validation that's already happened through a number of other nuclear power plants over the years.
There'll be many more questions for you in a moment. Thank you very much indeed. And now we move to fuel cells for power and heat, and we're very pleased to have Professor Nigel Brandon, the Director of the Energy Futures Laboratory at Imperial College here in London. Nigel is a very active fellow of this academy. He was awarded our silver medal in 2007, and following a 14-year career with BP and Rolls-Royce, he joined Imperial College, where he holds the chair in sustainable development in energy, and he's the director of the EPSRC Hydrogen and Fuel Cell Supergen Hub, the UK's national research hub in the field. And he will talk about the latest innovations in fuel cell technology. He will assess the current costs and performance, and will discuss the role that this technology can play in low-carbon energy systems. Nigel.
Or do I just keep going? It's all very clever.
You might have to.
There we are. Okay, very good. Well, thank you very much for the introduction and for the opportunity. I must remember to stand in front of the microphone. For the opportunity to talk to you this afternoon. As was just mentioned, I'm director of the Hydrogen and Fuel Cell Supergen Hub, which is a Research Council-funded initiative, and we have downstairs available over drinks later a chance to see some of the work that's taking place in that, and Dr. Chloe Stockford, who's the administrator of that hub, is here as well. So I do recommend going and talking to her later. In the time I've got, assuming that you don't all know what a fuel cell is, I will give you a very quick kind of introduction about what one is. I'll try and tell you why you should be interested in them. There have been many false dawns with fuel cell technology, and so what I'm going to try and do with the presentation this afternoon is indicate to you, I hope, that we are moving beyond the false dawn and we are engaging in the start of a commercial rollout of these technologies, and in particular for the provision of stationary power and heat. In that context, we'll try and talk a little bit about why they might be of interest, and it picks up on some of the conversations that have already taken place for this morning, earlier this afternoon around gas, for example, and hydrogen. So I could spend probably half an hour talking to you about this slide, but I'm going to try and talk to you about it really quickly. These are two types of fuel cells, a solid oxide fuel cell, which is this one, and a polymer electrolyte membrane fuel cell, which is this one. If you look at fuel cell cars and fuel cell buses, they tend to have this type of fuel cell in them. Some types of stationary fuel cell, particularly in Japan, have also had quite a rollout of this. This is a higher temperature device. It operates at somewhere between 500 degrees centigrade and perhaps 800 to 900 degrees centigrade, depending on the type of materials used. And this is generally a low temperature device running between about 80 degrees centigrade and 120. In both cases, the same principles apply. If I look at the high temperature fuel cell, what we're doing is we're putting fuel on one side, shown here as hydrogen, and the fuel cells love hydrogen, but they don't have to use hydrogen. But here we're going to use hydrogen as our example. And on the other side we put an oxidant, which is almost always these days oxygen from air. And this particular type of technology, the solid oxide fuel cell, has an oxygen ion permeable membrane, which means that oxygen will pass across the membrane from the air side to the fuel side, where it will combine with the fuel to produce, in this case, steam. By separating, if you like, this oxidation reaction, by separating the combustion process into two sides of a membrane, we can capture the electrons that are transferred in this combustion reaction, and we can pass those around an external circuit, and that is a flow of current. And we also generate a voltage because this reaction has a thermodynamic driving force, gives energy of reaction, and that translates into a voltage. So we have a voltage and we have a current, so we have power. And we do this without, if you like, classical combustion. So this electrochemical process is very efficient and gives us a high efficiency device. In the low temperature fuel cells, the same principles apply, except now the membrane is a proton conductor, not an oxide ion conductor. Protons transport across the membrane, and our reaction product forms on the air side as liquid water. So that's what a fuel cell is. There are many different types of fuel cells, from high temperature solid oxide fuel cells to intermediate temperature solid oxide fuel cells. And again, I'm delighted to say that Mark Selby, who's sitting here towards the front, raising his arm, who's the technical director of Ceres Power, which is a UK fuel cell developer, will be downstairs as well. And Mark has kindly brought along some of examples of the technology that they're developing, and which I shall mention, and also can show you a video of how they manufacture these in their factory and production process in Horsham, to the south of London. We also have phosphoric acid fuel cells and polymer or alkaline fuel cells. Every one of these types of fuel cells are now being developed commercially, and they have different advantages and disadvantages for different applications, but all can now be available commercially. And indeed, you can go onto various websites and buy yourself, as we frequently do at the university, these types of fuel cells and play with them in the lab whenever you want to now. The other key thing then is not only what the fuel cell is, but what's the fuel. And this sort of graph helps perhaps paint a picture of why different fuel cells integrate better with different types of fuels. It comes from a very well-regarded paper by Brian Steele, who published this paper in Nature some years ago, a very eminent figure in the fuel cell field. And what it says is that if you've got high-temperature fuel cells can generate electricity from a wide range of fuels. If you put natural gas into a fuel cell, what the fuel cell does is it turns that natural gas into hydrogen and carbon monoxide. It reforms. We also have an SMR, but in our case it's a steam methane reformer. And the reforming reaction takes the hydrogen from the methane and turns it into a fuel that the fuel cell can use. Of course, that takes heat. It's an endothermic reaction. So these high-temperature fuel cells are very good at using a wide range of fuels, the heat of the fuel cell being recuperated to drive that endothermic reforming reaction. If we want to use a low-temperature fuel cell, perhaps like a polymer electrolyte membrane fuel cell, we need to supply that with really quite clean hydrogen. And Graham indicated earlier that there were some issues around hydrogen purity for fuel cell vehicles, and that's true. So you have to go through quite a more complex process if you're making it from natural gas. Of course, if you're making it by electrolysis, it's clean enough to go straight into that fuel cell in the first place. So the integration of the fuel in the fuel cell is important, and as far as I'm concerned today, I'm going to focus in particular on natural gas fuels. That natural gas, we would have absolutely no problem if it had hydrogen blended into it to a significant extent, should that happen going forward. So why are we interested in fuel cells? We're interested because they are efficient. There is no device of equivalent scale that is more efficient for making electricity from our fuel than a fuel cell. So a fuel cell is an energy efficiency technology. It may be a renewable technology if we put a renewable fuel into it, but fundamentally the motivation is energy efficiency and the flexibility to operate a device whose efficiency goes up at part load rather than down. Hydrogen can be used as a fuel, but so can a wide range of other fuels, and as I say today I'm going to mostly focus on natural gas. Efficiency for a small system at the sort of kilowatt scale, the type that Ceres are developing, for example, is approaching around 50% now of chemical energy out to AC power out, chemical energy into AC power out. That's extremely high for something at that size, through to 60, perhaps to 70% for the larger systems where we integrate these devices with a gas turbine of the type that Rolls-Royce are now developing with LG as part of Rolls-Royce and LG fuel cell systems. Not often spoken about today, but one of the original drivers for this technology was the very low levels of NOx that it produces. That remains the case. Very low levels of particulates. They're mainly quiet and largely vibration-free, which gives them enormous siting flexibility. You can put them on the tops of buildings or into basements and so on. And perhaps in this audience we should not forget that the UK has a strong track record in this technology space, not only in the academic sector but in the industrial sector with companies like Ceres, Rolls-Royce, Intelligent Energy, AFC Energy, Johnson Matthey, amongst others, all very actively developing the technology. So this is an example of the series approach. This is a 1 kilowatt metal supported solid oxide fuel cell for a micro CHP unit, and you can learn more about that downstairs. These are some Bloom Energy. These are American based 100 or 200 kilowatt generators which are used with a lot of server farm and warehouse applications. These are some of the Japanese units which I'm going to mention a number of times, part of a program in Japan for the deployment of micro CHP units, where there are now over 60,000 of these purchased by customers in Japan. This is an example of the 2.8 megawatt molten carbonate fuel cell that's being developed by Fuel Cell Energy in the US and POSCO Energy in Korea. Worth noting that just opened is the world's largest fuel cell plant. That's a 59 megawatt plant in South Korea, comprising 21 of these molten carbonate fuel cells. So I'm going to talk about heat. Heat was mentioned before as one of the kind of unsung challenges, and really fuel cells for power and heat is about taking carbon out of heat. And I'm going to talk about it with natural gas, but if we put in a lower carbon fuel, whether it's got hydrogen in it, for example, or whether it's synthetic natural gas, or whether it's biogas, these are all consistent with the message. It's just that the carbon content goes down even further than the efficiency gain you gain from putting natural gas into the technology. And as was indicated earlier, heat is a real challenge. It's our biggest contributor to CO2 emissions, and it's a particularly tough decarbonisation challenge. Roughly half of heat is used in the residential sector in our homes, and so we're going to focus on that, but we mustn't forget, of course, manufacturing and process heat, which is also a tough challenge. How do we heat our homes? So this is some historical data on central heating fuels, and the green lines here, if you can see them, are natural gas. So we are primarily heat our homes with natural gas, so natural gas is the fuel to focus on. This is a vision in Japan of the kind of low carbon home of the future. This is this Any Farm program that I'm going to mention a number of times. I'm going to mention it because now we have over 60,000 units purchased by consumers in Japan of this technology. Now these are still quite expensive units, but nonetheless people are buying them and installing them. They're still expensive after subsidy. After subsidy today they're about £7,000 a system. No, nearer 10 actually after subsidy. They're about 15,000 without the subsidy and 10 after. So still relatively expensive today, but 60,000 people have purchased them, and we might explore that in questions if you're interested. So this is the Japanese vision, a micro CHP unit in the home connected with solar power, some form of control system and so on, and exporting power to and from the grid. So what's the argument here? What's the logic for micro CHP? It's a similar logic to effectively a heat distribution system, but you can install it without having to go through the complexity of retrofitting a heat distribution system. So if you want to combine heat and power system and you haven't put one in when you've built your city or your wherever your buildings are, it can be a very expensive retrofit option. The idea in micro combined heat and power is that you have, say, in this case, a micro CHP fuel cell system in your home that takes in natural gas, say, it generates electricity at about 50% efficiency, it captures the balance of the unused heat locally and can recuperate that within the home. Of course, traditionally, and certainly in this country, we're rather bad at capturing heat from centralised power stations, so most of that heat is lost. We lose a little bit more in transmission, and we capture, therefore, much less of that energy as electricity in the home. I don't know if that's me, but I'll put that there. There are a range of micro CHP technologies, not just fuel cell technologies. You can get gas engines, you can get Stirling engines, you can get different types of fuel cell technology, a PEM fuel cell technology, and an example here of the series power solid oxide fuel cell technology. These are distinguished by having different electrical efficiencies. And that's important because it means they generate different amounts of heat per units of electricity. A Stirling engine is about 12% electrical efficiency, so it generates about 8 to 1 units of heat per unit of electricity. A gas engine is around 3 to 1 heat to electricity, a PEM fuel cell about 2 to 1, and a solid oxide fuel cell about 1 to 1 or even under 1 to 1. And that's important because when we look at, for example, the sorts of load profiles we're trying to deliver against, and this is some measured data, we find that, of course, there isn't always a correlation between the heat demand and the electrical demand, and so we need to be able to operate our unit at different times of the year. We need to operate our unit flexibly. And it turns out that the critical economic driver for micro CHP is the heat to power ratio. If we're not allowed to dump the heat, we wouldn't want to dump the heat, and indeed we're regulated to be allowed to not dump the heat. That means if we, in a heat-led device, if we have to produce too much heat, we have to switch the unit off. If we're switching the unit off, we're clearly affecting significantly its economic value and its value to the consumer. We also affect significantly its CO2 benefit, and this is some analysis for different types of micro-CHP. The details here, I'm afraid, in 15 minutes I'm going to have to swiftly move through. I just want to leave you with a couple of take-home messages from this. Firstly, there's a paper down here if you're really interested, and I referred you to it, or you can come and see me. This is a gas engine, a PEM fuel cell, a solid oxide fuel cell, a Stirling engine. This is the CO2 saving if you were to use this device operating on natural gas compared to plugging in, taking grid electricity at 450 grams of CO2 per kilowatt hour, which is the current DEC long-term number, and a condensing boiler for the rest of the heat. And this is CO2 saving. This is about 1.5 tons of CO2 per household per annum. What you find is that across a range of households with a range of thermal demands, your SOFC micro-CHP is saving you somewhere between 1.2 and 1.5 tons of CO2 per household per year over the reference case, which is the current way we do it. A Stirling engine isn't saving very much because a lot of the time you can't switch it on. A PEM fuel cell is okay at bigger buildings, but it's less good with small buildings, and a gas engine somewhere in between. So this is an important message. It says that the high efficiency of the SOFC in a heat-led mode actually saves you a lot more carbon across a whole more range of dwellings than these other CHP technologies. We can also look at some of the system benefits of this, and this is some work that's going on at the moment to inform a briefing paper that the Supergen Hub is producing on the role of hydrogen and the role of fuel cells in low-carbon heating. And this is some analysis from colleagues at Imperial College, Phil Grunwald and Adam Hawkes. And what they're trying to do here is look at the benefits that fuel cell micro-CHP might bring to the system as a whole. What they're plotting here is the normalised demand of electricity for the whole of the UK system in the coldest week of the year, measured demand, against the output from an SOFC unit that was connected into a household based on measured thermal demand for those households. And what they're saying is if that thermal demand was met by a micro-CHP unit, a fuel cell micro-CHP unit, this is the electricity the fuel cell would generate on those different days of the year. And there's a strong correlation. And this is extremely helpful. This is the opposite correlation of a heat pump, for example, where the maximum demand from the heat pump is also correlates exactly with the maximum thermal demand. So just when you need the maximum heat, you need the maximum electricity, and that's going completely the wrong way. What you want to do is this solution where as the load of the system on the national system goes up, the fuel cell output goes up. So this is an extremely helpful correlation. A heat pump would go the other way. Of course, heat pumps are an important consideration when we look at low carbon heating options, and we're interested in them because we're trying to align them with the decarbonisation of heat. And again, this is based on this similar analysis. This is looking at the load over 46 households over 2 months of a winter period based on measured data. And it's a load duration curve, so this is load over these households against time. And it's a cumulative load. So for a small number of hours we have a big peak, and for a larger number of hours we have a smaller amount. This is the baseline with no heat pumps, electrical demand. And this is measured data putting 20% of those homes with heat pumps. And what, of course, we see is a sharp increase in the electrical demand because, of course, we're now putting more burden on the electrical system. If we say, well, we don't want that, what we'd like to do is to keep our 20% of heat pumps, but we also fit 50% of fuel cell CHP systems into those homes. What you find is that the fuel cell generates at the same time that the heat pumps need the power. And this is, again, a very good fit. It means that we are not increasing the peak load on the system to a significant extent. And the cost of electricity infrastructure, as my expert colleagues from National Grid and elsewhere will testify, is quite heavily driven by peak load. We're also not increasing the load significantly on the low voltage distribution system, which is another significant saving. So there's a synergy between these two low carbon heat technologies, which is very attractive. And finally, this is looking at the amount of electricity that would be generated from a fuel cell CHP system compared to the amount of electricity that will be generated from a Stirling engine, based on measured data against different amounts of heat loss from a home. So if we go to more insulated houses, we actually can generate more electricity from the fuel cell, and that's important because as we go to more and more better insulated homes, this technology is shown to become a better choice than other CHP technologies. I can see the chairman eyeing up his watch, so I must rush on. This is current status then, just a few comments on this. If anyone wants to look at where fuel cells are at the moment, there's a good website, which I think is still open, though I know that its lifetime is limited because Johnson Matthey funded and are moving funding elsewhere. But this looks at the tracking of the sales of fuel cell systems over time. And this is looking at the sales in megawatts in the stationary sector and the portable sector. And firstly, if you don't follow this space, you might be surprised to see that we're now, in last year, you see 200 megawatts of sales. Now, in terms of global energy demand, that's not that significant, but in terms of an emerging sector, it's really quite significant. Where are the units being sold to and installed? Asia, primarily, and North America to some extent. And we've still got some catching up to do in Europe. And finally, what about cost? It's very difficult to get your hands around cost. One of the biggest data sets we've got is the Japanese Any Farm program, where they've now got 60,000 units deployed. This is based on a paper from some colleagues at Imperial College in 2012, and I've added myself the 2013 data point there. This is showing costs down over time as these technologies gradually go up in volume. The estimated target rollout for 2020 is 1 million units, and that will put us down at around $10,000. Now that's a lot of money, but actually it's not that much money when you compare it to a heat pump system, which is the other low carbon technology. So that's interesting to see the cost curves coming down a learning rate of about 20%. What about the larger systems? If you go for a larger system, the pounds per kilowatt, these are dollars per system, which is about dollars per kilowatt. $1,800 a kilowatt for that 2.8 megawatt molten carbonate fuel cell. Lifetime's still a challenge there. It's about 5 years rather than 10. So there is an implication on cost. Bloom, which make the solid oxide fuel cells, are about £5,000 a kilowatt. Clear Edge, which make the phosphoric acid fuel cell, used to be UTC Power, £3,300 a kilowatt. If you talk to Mark later, and I've heard his colleagues speak, they see a route to $500 a kilowatt for stack cost for their technology. So this is based on the current technology and doesn't allow for some of these step change innovations to come through. So I think we're living in exciting times. I hope I've given you a sense of that. Do come down and talk to us later over the display. Thank you very much.
Yeah. Well, thank you all very much indeed. Fascinating. Now, let's open the questions. Yes.
Hello, my name's Duncan Price from Burco. I've got a question about the Isla project. Thank you very much for a fantastic presentation. I was fortunate to work on Isla on a community wind project many years ago. So I happen to know it's got a very weak grid. And I just wondered on your views about whether you see the rollout of that kind of technology being small scale and having to cope with those weak grids, or large enough deployment that you can invest in subsea cables.
Yeah, we see this as being probably one of the rarities of trying to connect a tidal energy grid at 10 megawatts into what is basically the last available 10 megawatts in quite a delicate grid, as you say. There's no point in continuing to do these kind of demonstration scales. So our plans actually are towards the north of Scotland. The strongest tidal flow has been Pentland Firth, so that's easily 0.5 gigawatt mainland connected, of which grid agreements are in place and upgrades are happening. A couple of advantages though that we need to outlay is the predictability and therefore the potential contribution of tidal energy to whether it's base load or whether it's capacity sharing. Wave and wind actually has quite wave, wind and solar actually have quite an interesting relationship that you can draw on for sharing of capacity, because it's very rarely sunny, windy and wavy all at once. Tidal, however, gives you that base load, but over a large array, the kind of cyclic and sinusoidal energy production profile that I showed there is just one device at one point in time. By the time you have 10 or 100 units of those, that ripple will be smoothed out because they'll not all be seeing the flow at once. So, sorry, cut to the chase. We do see it being far more substantial. and actually we're pursuing it more along the lines of our offshore wind and onshore wind grid infrastructure requirements.
Yes, Barry. Yes.
Question for Fiona. For Fiona, Graham Cooley from National Power. I'm interested in how you integrate nuclear generation into a low carbon future. How do you get nuclear out of base load and into the mid-merit, or even be able to modulate it very, very quickly? I mean, you could, you're looking at smaller modular reactors now. Does that strategy actually help you with flexible operation?
Yeah, there's a number of there's a number of nuclear systems now that are being developed that actually are load-following systems. So that's a bit of a new thing for nuclear in terms of where we've been in the past, because of course a lot of the nuclear systems very much need around, as you say, 2 to 3 days to actually get them up to full power, and then of course powering back down again takes quite a few days for that to happen. So one of the key concepts now is to actually get reactors that are a bit more flexible, not in terms of start-up, but once they're actually up and running, being able to load follow an awful lot easier. So there's a number of designs that are being looked at to take that into account. And I think that looking at small modular reactors and even some of the pressurised water reactors that could be small modular reactors going forward could do that. They could exactly load follow. So I think that's something definitely that could be linked in terms of beyond baseline. But it wouldn't be in terms of starting up and closing down. It would be once you're operational, can it load follow?
Okay. Yes. Microphone here.
Fiona? Can I just ask, in respect of the small modular reactors, whether there's any benefits or disbenefits in the molten salt reactor concept, particularly using the kind of molten salts that are suitable for use of thorium?
Okay, good question. In terms of the, so that there are a number of molten salt reactors that are currently being looked at, both in terms of small modular systems and also as a large nuclear power plant. And there's a thorium molten salt reactor that's actually been looked at as part of the Generation 4 nuclear power plant reactor technology. But in terms of small modular reactors, I think that where molten salt systems will come into their own is very much around actually looking, as well as electricity generation, actually looking at how it can help with high intensity process heat, and also other aspects associated with large plants that actually require various other heat applications. Also in terms of actually looking at desalination plants and other opportunities associated with that. So I do think that there's a lot of advantages associated with what the thorium type reactors could actually offer up. That being said, there's still quite a lot of research that needs to be done for that type of system, and I think that in order for it to actually see its true potential, it would need to there would need to be quite an intensive R&D program put in place in order to actually take that forward. So my view would still very much be that in the short term, it's probably going to be a small modular reactor that's based on existing proven technology, so PWRs. But molten salts, I think, is something that could have its day at some point beyond the next decade.
Thank you, Fiona. Yes.
Thank you very much. Richard Coakley, it's a question for Fiona on the SMRs. Fiona, the safety case for an SMR, what's your view with regard to the increased simplicity, if there is any, in the safety case, and the speed with which a safety case can be made for an SMR, and proximity to civilization of these units? Very interesting.
So with any nuclear power plant, and if you look, let's just take the UK as an example. If you look at the overall regulatory regime that any new nuclear power plant has to go through, it goes through a generic design assessment, then it goes through regulatory permitting, tongue-tied, and then it also has to go through the full licence application on a particular site. Now, with any first-of-a-kind nuclear power plant, whether it be an SMR or whether it be a large nuclear power plant, it would still have to go through that same regulatory regime. So I think that the safety case itself for a first of a kind, no matter whether it's an SMR or a large nuclear power plant, will probably take the same amount of time. Once you get to the stage that you've beyond that first of a kind and you start to get to multiple units, that becomes an awful lot easier at that stage. And of course, if you're talking about SMR technology, there is an assumption that there maybe be more of these in comparison to maybe a large nuclear power plant. So it'd start to get easier as time moved on. But first of a kind, it would take the same amount of time.
Nigel, why don't you look ahead for a few years and tell us when commercial fuel cells on a scale will be available and in what sectors?
Well, I think the key is that they are available now. You can go and buy, you can place orders for these things. I think it's more a question of how do the costs continue to come down, because it's there are still cheaper ways of generating electricity, but they are commercially available. So as we saw from the Japanese experience, as we continue to deploy more and more of these units, there will be some cost reduction from learning and learning by doing, and we would expect that, and that will definitely happen. If we look at that technology, if you take that learning rate down, you'll be at $10,000 a system by 2020. But there are larger systems that are going to be considerably cheaper in terms of dollars per kilowatt. And then there will be some step changes, and go and have a look at the series technology downstairs later, and you'll see an example of how through clever use of materials and some clever engineering, you can offer a significant cost reduction. So I do see some steps down as well. So I think that, as I say, you can buy these things now. They will get cheaper, but there are also some other exciting things just on the cusp of going to product.
Good. I think we're going to draw this to a close. So can you give a big hand for Fiona, Nigel and Barry for their contribution?